So in the previous lecture, we talked about virtual address spaces and how they are used for different processes, such as process A and process B. And last time we also, discussed that core, data, and heap, they will be individual for each process, pretty much, unless it's some shared library wherein we can share the same code across different processes. So in general, they're different, but some pieces can be also shared under some circumstances. So now every address that you see in your program, it's a virtual address. It's not a physical address. So that's very important, right? So whatever you write in, whenever you want to write your program, and you can actually try to compile this program. This is a piece from your textbook, and you can just compile and run this program. All these addresses are virtual, not physical. So in fact, not only in the C program, all addresses are going to be virtual, but in whatever assembly code we have, whatever CPU instruction we have, they all deal with virtual addresses. At no point we deal with physical addresses directly. So virtual to physical translation happens internally inside the CPU, but not by us, right? So yeah, so we have to set it up. The operating systems has to set up this mapping, but this is done by the CPU internally. And the CPU itself, from the user perspective, the CPU deals with virtual addresses, not with physical addresses. Now, it will actually, eventually it will access physical memory, but that's a different story. But the address that you supply is always virtual. So you can compile this program, run it. Normally, in the past, when you run multiple instances of the same program, you would actually find that they're running in the same, address space, so to say. Virtual addresses are the same, but remember that virtual address spaces are different, right? So even though one address is the same as another address in a different program, right? So, but they're actually two different virtual address spaces. So this is why it's totally fine that they are the same. Now, of course, nowadays, that's not going to be true if you run a program, let's say on Ubuntu or in some other modern distribution. It's very likely that you have address space layout randomization, something that I also mentioned our last lecture. So when address space layout randomization is enabled, you have your addresses randomized. So even code addresses, data addresses, they will all be randomized. Okay, so just to give you an example, if I also write a program where I want to just print a heap address, for example, I'm doing malloc of a simple integer and just do printf for this pointer. I will have two instances of the same program. I guess in the past, it would not be unusual to see the same address because this is two different virtual address spaces. But nowadays, because it's also randomized, it's very likely that you will see two different addresses, just like I see in this, just like you see it in the screenshot. So whenever you run it, it's also going to be randomized. And every time we're going to get a unique address. Okay, so heap addresses are also different, right? So they can also be randomized. So now, go ahead.
What's the purpose of giving him the virtual address and not the actual memory address?
What's the purpose of it? Well, remember that the same physical memory has to be shared by multiple user programs. So now one user program may not necessarily be a good program, right? So it may be a buggy program, it may have some bugs, it can be really, it can even be malicious, right? It can deliberately try to access someone else's memory. So unless we have some way to separate, to isolate one memory from another, one program from another program, we cannot prevent any, we cannot prevent malicious behavior. Does it make sense? So we have to somehow isolate it. So now the question is, how do we isolate? That's a different question. And historically, there were other approaches, like for example, nowadays you would use paging, but there were other approaches such as segmentation. But segmentation can also be viewed as some sort of virtual memory, right? So yeah, it would kind of give you a segment of memory, but again, virtual address space is not necessarily going to be the same as physical address space, because there can be different offsets, different bases, right? So again, even with segmentation, that is not necessarily guaranteed to be the same, right? So the fundamental problem that we are trying to solve here is isolation. So one program has to be fully isolated from another program. I mean, at the very least, we should not allow unrestricted access to the physical memory, right? So that would, or something that would otherwise happen. Does it answer your question?
Yeah.
Okay. So now let's say we run multiple processes, and for example, in fact, for simplicity, we can treat it as different programs, but remember that each program can be actually multiple processes. Like, for example, this Google Chrome, right? It can be multiple processors for each tab. So for each process, you're going to have your own page table, like in case of using virtual memory, right? So, and this is one approach. Another approach, I said segmentation, but this is no longer used by modern operating systems. For simplicity, you don't need to worry about the implementation right now. There is some way to translate virtual address to a physical address. The exact mechanism, we'll talk about this later, right? So that's not something that we should be concerned right now. So one way or the other, there is some mechanism to translate virtual to physical address, and the special unit, a memory management unit, is going to do that. So you can see MMU, this stands for memory management unit. It's going to translate virtual to physical address. Again, the exact mechanism of translation is not important right now. There is some way to translate one virtual address to a physical address. So the CPU will deal with virtual addresses, memory management unit will translate it to physical address, and this is where you're going to actually eventually access memory, right? This is the address that you're going to put on the memory bus later, right? So when you want to retrieve this piece of data. So now in the OS, we will manage this memory by setting up virtual address translation for each program. We will allocate memory and so on. So now I have a question, right? So clearly we can translate virtual to physical addresses easily. Can we do the opposite, physical to virtual address? Any guesses? So let me give you a hint. Okay, go ahead. Yeah, so you can have multiple virtual addresses corresponding to the same physical address. Like as an example would be shared library, right? One process thinks that this is this virtual address, maybe another process thinks that it's a different virtual address, but they all point to the same physical memory where you put your code, right, for that shared library. So yeah, So yeah, so in general, no, right? And in general, there is no mechanism to do translation, and one of these reasons is because there is no one-to-one correspondence, because multiple virtual addresses can correspond to the same physical address. Now, the opposite is not true. Virtual address will only correspond to one physical address, right? So that's that's how this translation works. We cannot have multiple physical addresses for the same virtual address. Did somebody ask something? Okay. Okay, so no, but that's not entirely true, to be honest, because in Linux, for example, you have an identity mapping. So in some range of virtual addresses are reserved to map the entire physical memory. So in other words, you have a virtual address for in this program, but also inside the OS kernel, you have an easy way to access any physical memory that you want by having some sort of identity mapping, right? Where you can have one virtual address corresponding to physical memory address. So it can duplicate, right? So there might be already some mapping to this physical address, but doesn't matter. You just want to have a simple way to access your physical memory. And because there is no way for a CPU to specify a physical address, you can only specify a virtual address. In some cases that can be very helpful, right? So because sometimes you want to initialize some physical memory, and you especially when you deal with IO devices, they need to know the physical addresses rather than virtual addresses, and this is why it can be useful. But again, this is an exception. This is not absolutely necessary. This is just the way that Linux implements it. In general, there is no way to translate it. Even in Linux case, we can translate our virtual to a physical to a virtual address, but it's just some virtual address that the kernel has, but there might be many others, right? So in user space, not in user space, maybe also inside kernel, right? So it just gives you one virtual address, but not others, right? So you don't have this general way to translate it. So, but it's important to note that multiple virtual addresses can correspond to the same physical address. I think that's one thing that is crucial here. Okay, so now the next, okay, go ahead.
I just wanted to ask about a couple slides ago, the code.
Yes.
It says a test, and it's I assume it's printing both the pointer, the value of the pointer, and the physical address.
This is virtual address, because remember I mentioned in the very beginning that in the C program, whatever you deal with, it's always a virtual address.
Oh yeah, but what's like the meaning of 13821?
Oh, by the way, just a reminder, we don't have any remote connection. Someone is again trying to connect. Just a reminder, right? So, okay. Sorry, can you repeat?
What's the meaning of the number 13821?
Oh, that's just this process was run in background and just an identifier process identifier, right?
That's the actual perspective.
So the address itself is whatever starts with 55, right? So this or 56, right? The next one. So I mean, yeah, again, they can be the same virtual addresses, because remember, these two different virtual address spaces, right? But in this particular case, they happen to be different because the operating system also randomizes them, right? So this is why we see every time you run this program, you see different address. But in general, it doesn't have to be like this. But this is because for security reasons they do randomization nowadays. Does it make sense? Okay. So how does the OS help multiple processes share the same CPU? Remember, we have just in a simple case, we have just one CPU and one core even how do we share that core across multiple processes? Well, you know, especially, well, you can argue that nowadays we have even simple system. We have like 8 cores of, you know, even your laptop is likely to have multiple cores. But doesn't matter fundamentally because you still may have like 8 cores and 100 programs, right? So how do you run this multiple processes, like which is significantly, their number is significantly higher than the number of cores that you have. Or it doesn't have to be significantly higher, just higher, right? Not the same, not the same number. So how does the OS help us to run this multiple processes? Well, we have to solve multiple questions here, right? So so let's assume that we run 2 processes on a CPU, and just for simplicity, assume that we just have 1 core, 1 CPU, and yeah. By the way, is it? I don't know. Is it overlapping there? Okay. Yeah, so let's assume that we have 2 processes, they run on the same CPU, and let's take a look what will happen there. So we have process A, then we have process B, right? So let's identify some questions that we want to answer. So the first question is, what if the process is doing something undesirable here, right? So shouldn't damage the entire system because there are multiple processes running on the same core, on the same CPU. So what if something bad happens here? So we will get to the point what bad is, but let's say you call some legal instruction. So what are we going to do here? So the second question is, how does the OS get to start running here? So somehow, I guess we want to switch at some point from the process to an operating system. So how do we actually want to start running here? Especially if there is an error, so what are we going to do, right? So what is the mechanism for that? So the third question is, how do we ensure that A resumes execution at T2 as it had not been taken off as the CPU at T1? So A was running initially, then, you know, for whatever reason, it was descheduled, and we scheduled another process B. So how exactly we switch back to those? That's a different question, but you know, somehow B was scheduled. So how do we ensure that A, whenever it resumes, it doesn't even notice that it was suspended, right, previously? So it's like your program is not designed in a way that you don't actually, whenever you write your program, you don't think that it can be suspended at some point, right? So you just write whatever you want to execute, and that's it, right? You don't even think that it can be overlapping with some other process, and it can be time sharing a CPU with some other process. So that's another question that we want to answer. So somehow we have to resume the entire state so that the original process doesn't even notice anything. Well, maybe unless it wants to measure CPU time, system time, but you know, unless it's doing something really special, it won't notice that. Okay, the fourth question, how does the OS decide which process to run next? You know, we have an example with 2 processes, but is it the only thing that we may have, just 2 processes? What if we have like 10 processes? How do we decide which process to run next? So that's another question that we want to answer. Okay, so let's go back to the first question. So what undesirable things a process might do, right? So what are those undesirable things? Well, I already gave a hint to that we can have some sort of a legal instruction. But what does it mean to execute an illegal instruction? Well, maybe one case is when you call the instruction that doesn't even exist. That's a possibility, because after all, you can put some garbage in your binary code, right? So, and it doesn't even have to correspond to any legal instruction, and just try to execute it, and most likely it will fail, right? So, but won't do anything meaningful. So that can be an illegal instruction. So, but another question, I think even more important, so should we be allowed to execute any instruction we want? So should a process be allowed to execute any instruction it wants? Okay, so I see someone says no, right? So, but why is it no? Okay, so yeah, so what can you elaborate on this? Yes, so but give a specific example, maybe give a specific example. Well, let me give you a hint. Well, let's look at, I mean, there are multiple things that may happen. But let's say you execute some instruction that can change virtual to physical mapping, like something like this, right? So let's put it this way, right? So what will happen? Yeah, so you can potentially do something bad to a different process, right? So therefore, only the OS should be allowed to execute that instruction, not an arbitrary process. So other examples, right? So in addition to this, so what if the program were allowed to like execute hold instructions to shut down the CPU? Just 1 second, right? So that's another thing that we shouldn't allow. Because this CPU is not, it shouldn't be shut down, right? We run one program, then another program, then we go back to the operating system. That's certainly not allowed. Also, I instruction. What if your program? I guess it's closer to what we already mentioned. So what if your program executes some I instruction that will perform some write on your hard disk, and you will potentially access some file that you don't have permissions to access, right? So that would be really bad, right? So again, this is something that we shouldn't allow. Okay, go ahead. There was a question, right? Yeah, so as an example, it's hard disk, right? So you well, it's a little bit tricky because I instructions are some sort of legacy instructions nowadays. Yeah, but let's assume still in the past, I mean, certainly things like floppy disk or hard disks we would use I instructions in the past to access it, right? So if you use I instructions for that, you can specify some sector on your hard disk and override that sector with some garbage, right? And let's say you corrupt some file that, like a user, unprivileged user corrupts, like let's say you have running on the server, you don't have administrative privileges, you just have a user permissions, and you corrupt some system folder and override some system programs. That would be really bad, right? So that would break all security assumptions. So, okay, so let's recall what system instruction set is. So by the way, I assume you know that it's instruction set architecture, right? So Yeah, and I'm gonna just say instruction set for simplicity, right? So we have hardware, right? And then on top of hardware, we have two sets of instructions. One is the system instructions, and another is user instruction. So your applications libraries can only use user instructions, but the operating system is also allowed to use the so-called system instructions in addition to user instruction. Of course, it can use user instructions like a regular jump instruction or regular move operation, right? So those are common for both user programs and the operating system. But you cannot use in a user program something that would change virtual memory state, or something that would change IO state and so on. So in fact, when you look at the documentation, if you look at manuals, you'll find that there is a system instruction set manual, right? And or there is also user instruction set manual. So if you go to the Intel or AMD website and download manual for the CPU, for this CPU architecture, you'll find different volumes also, right? So one volume is for user instruction set, another volume for system programming. So also the same deal, I guess, for ARM and other processes. So typically they keep it separate. So what is the solution to this problem? Because remember, the problem was that our program can execute some instruction that is not allowed to execute, or or it may be some illegal instruction entirely, right? So why is it? So what is the solution here? Well, the solution is to use so-called traps. So your CPU is designed in such a way that upon occurrence of certain events, it will enter a special state and execute some special trap handler inside the operating system. So effectively, it will go back to the operating system, go back to the OS kernel, and execute some code there. So what are those events? So a process executes a privileged instruction is one event that we already discussed, right? Well, maybe the process or the OS encounters one of the set of errors conditions defined by the CPU. So any examples for that? So I think what if happens if you divide by 0, right? So that would be one example, so you cannot divide by 0. You want to probably generate some trap as well. So that's an error condition. So such events are known as traps. So how can you trigger traps also, right? So yeah, clearly one way to trigger it, because some condition happens, you access in privileged instruction, or you're accessing some illegal instruction, or you're doing something that would violate normal control flow, right? But you can also execute, you effectively can trigger this trap yourself, right? So you can artificially, so to say, trigger the trap, right? Because for some reason you want to go back to the operating system. So for that reason, we can use the int instruction. So that will actually artificially raise some error, or like maybe not a real error, right? And then you will execute the corresponding trap handler.
So int is still not perfect.
So that's I actually didn't ask this question yet, right? Yeah, so int is unprivileged, yes. So why is that?
Because it was used for to do certain system calls, as the slide says.
Yes, but my point here is, the reason why I ask this question, it's a little bit tricky question. It's kind of like a chicken and egg problem, right? So what causes a trap here? Executing int itself and then maybe saying, okay, there is something bad happened here, let me go back to the OS, right? Or int itself is fine, but it just still triggers a trap, right? So the answer is the second one, right? So, but I mean, you may wonder why, right? So, but we will look at this, and sometimes you have this kind of questions, and you are not fully sure what actually triggers a trap, whether it's because int itself is doing something invalid, or because it's some sort of fake interrupt, right? Or whether int is designed in such a way that it will trigger a trap. So we will look at this a little bit later during this lecture, and I will show you why it's still unprivileged instruction. So now the second thing that was mentioned is that why do we need this fake traps? Why do we need to artificially go back to the OS? Well, let's say you want to allocate some memory, you want to read some file from a disk, you want to write to some file to a disk, you want to do something to the operating system. So how do you deal with this, right? So how do you actually go back to the operating system? How do you use this operating system API? Well, that's for that reason we can use system calls. And int, this int instruction was actually used in the past to implement system calls. So nowadays we have a specialized instruction, so this mechanism is no longer used because the specialized instruction is faster and it's better to use it. But for a 32-bit processor, still, like legacy operating system would use int. So by the way, int may also look a little bit confusing because int stands for an interrupt, right? So and this doesn't look like I haven't talked about interrupts yet. So just to kind of clarify, sometimes those terms are a little bit confusing, whether it's an interrupt or a trap. Those are very close, closely related things. But there is one big difference, right? So I'll get to that in a moment. So a trap is something that is triggered inside your CPU. So that's some internal event, something that is internal to the CPU. You're trying to execute some instruction which is not supported, or you're trying to call to access maybe privileged instruction, something like this, right? Or maybe you're trying to divide by 0. This is all internal CPU events. But there's also external events, right? So those are known as interrupts. Well, in x86, it's a little bit confusing because the same mechanism is effectively used for both. And this is why they also specify int, right? So rather than trap. But, just remember that int is actually a trap, right? Not an interrupt. So examples of unprivileged instructions. This is move instruction in assembly, which would load or store data. A typical arithmetic operations, add, sub, jump, whatever you have, right? Maybe multiply, divide. All of them are unprivileged instructions. There's nothing, we shouldn't prevent a program from executing that instruction. So, but then there is some examples of privileged instructions. We already mentioned like called, in, out, and there are some others. So just to summarize, there are 3 ways in which traps may be raised. So there are 2 involuntary ways. So when we execute a privileged instruction, we may harm the other process, so therefore we have to trap that instruction. So second case is, certain types of errors that can happen within the CPU. You divide by 0 as an example. So you want to trap that as well, right? So and then there is also voluntary traps. You want to execute a system call. So again, there are 3 types, right? So what will happen when we have a trap? So the first thing that we're gonna do, we're gonna save a processor state, right? So because remember the program was executing something, and not all traps are fatal, right? So maybe if you are executing a legal instruction, that's a fatal trap probably, which will result in program termination, right, and so on, right? So you'll typically see some segmentation fault, or on Windows you will see some program encountered some error or something like this, some message like that, right? Yeah, so but not all error cases are like this. Sometimes there is examples when you lazily allocate some memory and you don't allocate it initially, but when you only allocate when you try to access some piece of memory which doesn't exist yet, right? Just one example, right? Like so-called lazy allocation. So it's not really a fatal error. It should be handled transparently, and therefore there is a possibility that we may need to return back to the program, right? So it's not really again, it really depends on the type of trap. And also in addition to this, like one other example is system call. That's also not a fatal trap, right? That's something that would, if we execute some OS event, like OS function, like read, write, or allocate memory, and then we want to go back to our user program. So there is nothing fatal about this trap, right? So therefore, the general idea, we want to save process state. Then we want to transfer control to the corresponding trap handler. By the way, this is done by the CPU, right? So this is done, it should be done by the CPU. And CPU indexes traps and assign it, each trap a corresponding vector. And then you have a trap table where for each vector you have a corresponding handler. And a handler is effectively a special function. It's not a regular function in the way that you write this function in the C language, but you can still, for simplicity, view it as a function, right? So for example, trap vector 0 can say, okay, it's a legal address. Trap vector 1 can say memory violation. Trap 2, illegal instruction. Trap 3, system call. So for all of them, you have separate vectors. So then it will jump to the corresponding address. In this table, you have effectively an address of this function where you want to jump to. And eventually want to restore process state and resume. So again, this is done by the CPU, right? So all these transitions should be done by the CPU. And specifically, most importantly, finding out what trap vector is, what address is, what function needs to be called, and so on. So one thing that we haven't considered yet, I mean, it's if we execute in some legal instruction, completely illegal instruction, like I said, garbage, right? Yeah, that's probably not good for both operating system or user program. That's certainly something that should not be allowed, right? But there's also cases like when it's a legal instruction, like you want to call a halt or in, out, whatever, or maybe you want to manage do some other memory related operations which require some privileged access. So those are privileged instructions. They are totally fine to be executed inside the OS. We don't want to trap them, because otherwise that would just slow down system significantly, right? We would kill performance of the system, right? We don't want to trap them. They're unlikely to happen in user program. This is like sort of error case. So we want to trap them in user programs, but we don't want to do that inside the kernel. But how does CPU know the difference between the user program and kernel? I mean, eventually it just executes a bunch of instructions reading in memory, how does CPU know that it's kernel or program? Any ideas? Okay, go ahead. Yeah, right. So we have dual CPU mode, right? So there is dual CPU mode. So modern CPU supports at least two modes. One is user mode, and the other is kernel mode. So sometimes it's also called unprivileged mode and privileged mode, as you mentioned. So the idea is that we only so if we execute a privileged instruction in user mode, that will cause a trap. If we executed privileged instruction in kernel mode, that will not cause a trap. That will be fine. So historically, there were actually more than two modes. For example, in x86, there were multiple even rings. I believe there was 4 rings. 4 rings of protection, so basically 4 different modes, but they were not actually used by by operating system, but by the vast majority of operating systems, at least something that we use nowadays, right? Like Linux or Windows. And most other CPUs just implemented 2 modes. So the idea here is that the CPU will keep a special bit indicating what mode is currently active, like whether it's a user mode or kernel mode. So and then effectively this way, if we are in user mode, if the current bit is user mode and we are trying to execute a privileged instruction, therefore CPU can conclude that it has to call a trap handler, right? So, and therefore this is how we're going to handle it, right? So let's kind of look how this happens, right? So remember that OS runs with the CPU and kernel mode, right? And OS is responsible to ensure that programs will run in user mode. So before we jump to any user mode code, we will have to switch back to the user mode. So the operating system has to do that. So how do we actually implement it? Well, remember that the operating system is pretty much the first program that you run, right, on your computer, except maybe firmware. So once you start, so it's the first software that you're going to run when you boot up. And at that point, that will run in kernel mode initially, right, in privileged mode. And from there, you can decide, okay, I'm going to switch to certain program, let me switch to user mode, and then jump to a corresponding function. Then in this program, maybe later, this program wants to call us to do some operation, like read some file from disk. It will issue a system call to the operating system. This is when it's going to switch back to the kernel mode. But see, we cannot, unlike the first case, when we can switch from kernel mode to any user program we want, to any others that we want, right? There is no restriction for that. When we switch from user mode to kernel mode, that has to be carefully controlled, right? So we cannot just allow a program to jump to some arbitrary kernel code. So we can kind of think of it as some sort of gates, right? And there are some checkpoints where we will verify. Like you go to an airport, you don't go directly to the airplane, right? So first they will make sure that you don't have anything bad in your bags, everything is fine, right? And only after this you're gonna go to the secure area, right? So when you leave the secure area, no one cares where you're gonna go, right? So it's up to you, right? So the same thing here. So once we switch we don't care where we're going to go to in user mode code, right? So it's it's up to the operating system to decide. Now, when the user program tries to go back to the operating system, that should only be done through special entry points, right? Which will be carefully verified. So where the operating system will have an opportunity to carefully verify everything, right? So to make sure that this program is not doing anything bad. So your textbook has this description how this dual CPU mode works in terms of the operating system, hardware, and the actual program, right? It's not fully precise, but let me get to this a little bit later. So the idea is that initially when the operating system runs, it will create an entry for a process list. It will allocate memory for the program. It will set up user stack and so on, right? So, and then finally, at this point, at some point, it will go to the user mode program, right? But in user mode program, we have to restore registers. Just for a moment, assume that we just gonna put some initial values because this program was not executing before, so therefore we'll just set some default values for registers, and finally jump to the main function, right? So while running this program, let's say we wanna issue some system call, and then that will trap into the OS. So now when we trap into the OS, we have to save some state of this program. The textbook says saves registers. That's not fully precise because let's just say we have to save some state, right? Not necessarily all registers that you have in your CPU, but at least some critical state. So what would be this critical state? I think a program counter would be one example, right? Like another maybe stack pointer. So now, but why do we need two different stacks? So why does it say that we need to save it to kernel stack? Any ideas? Why do we need the second stack here? So we've already had some stack in user program. So why do we actually save everything to kernel stack? Any guesses? So how do we manage stacks? So we manage it by specifying some value in a register. Okay, go ahead.
So that like when you want to receive the process again, like you have to pass state of that process.
Well, but why can't I just use user stack to save its state? Like, I mean, when I call main function, then maybe some full function from main, right? I have like I keep everything on stack, right? So all these program counters, like previous values of the program counters are going to be kept on stack, and then I can go back to the original place, right? So why can't I just keep using this stack to execute a trap handler? So what's so special about this trap handler? Because it's also fundamentally a function, right? So what is so special about the trap handler? Any guesses? So what mode the trap handler executes? Executes in kernel mode, right? So, but what stack we had? We had something that was for user mode, right? But the problem is not, I mean, that's not the primary problem. The kernel can still access user memory, right? So that's not a big deal, right? So it can still access any user memory, right? The problem, there is something else going on here, right? So it's somehow related to security, right? Yeah, so what if, so I mentioned that the stack pointer, you can write something to the stack pointer. That means I can basically write a null pointer to the RSP register just before I issue the system call. Let's say it's some malicious program or maybe some buggy program, and now it wants to damage the operating system, or maybe it's not doing it deliberately but just accidentally, right? And for some reason I'm moving a null pointer to RSP, right? So I'm corrupting the stack, right? Just before I execute a trap or right handler. So, and then, imagine like if I have to execute trap handler and then I'm relying on user stack, which is now a null pointer. I mean, it doesn't have to be null pointer. Null pointer I can at least detect there is something wrong here, right? So, but it can be some address which is very hard to verify, because remember, this is just the trap handler. I have to basically just execute it right away without any delay, right? I mean, I don't want to go and check whether this address is valid or not valid, right? So basically, I want to skip that. I want to just keep it the state of the program somewhere. But I don't have any reliable stack, because this stack that the user provides can be corrupted anytime the user program wants, right? Because RSP is basically changing the stack pointer is unprivileged instruction. Any user program can do that, and put whatever user stack it wants. So clearly, the user stack is unreliable. Therefore, I have to have a dedicated kernel stack. So the kernel stack, so once I have that it's a reliable kernel stack, I can save the state of the program. So because I know that kernel or the kernel stack will be programmed by the kernel itself, and the kernel will assume it's safe, right? So it will never specify anything, any bad address, right? So it has to be, at least that's our assumption. If the kernel is buggy, that's a problem, right? So that has to be, I guess, fixed, right? So there is no way around this. But well, there is some ways around creating different OS architecture, but that's a different story. But in general, we have to assume that the OS kernel is safe and that kernel stack is also safe. So once we save the state of the program, so now we clearly, aside from the program counter, we also have to keep the previous stack pointer, right? So the previous user stack pointer, because we have to eventually restore it. So we will at least keep these two values on kernel stack. So then we have to move to kernel mode. So that's basically flipping bit in the CPU, saying that now you're working in no longer in user mode, but in kernel mode, and then jump to trap handler. So this is done by hardware. So now the OS responsibility at this point is to execute a handler trap, complete this work of the system call, and then return from the trap. So once we are about to return from the trap, we will do the opposite. We have to restore the registers. We have to, we have to basically take them from the kernel stack, move to user mode, and jump to the program counter that is just after the trap, right? So remember, because this is not a fatal trap that doesn't cause anything bad. It's just a system call. So we'll have to just jump to the next instruction after the one that issued a system call. Just like calling a function, a regular function, pretty much, right? And then we're gonna go return from main function, from the main function in your program. Let's say we call exit, and exit is a system call. So at that point, the operating system will free memory of process and remove it from process list. Does it make sense? Any questions so far? Okay, so just to summarize, privileged instructions, traps, system calls, and dual CPU mode. So those are the mechanisms that we have to support, execution of multiple processes on the same CPU, right? And also to support both operating system and regular user programs. So we can switch from kernel to user mode anytime we want, from any place we want, but we can only go to kernel mode through special place, which are defined like either by system calls or by trap handlers. Because otherwise, user programs could have invoked any code in the OS, and that's bad, right? So what if this program is trying to call some kernel function which deletes another process? That's really bad, right? Well, unless this program is a is the kill program that kind of terminates program, but then you have to have the right permissions, like you typically have to call it under using the administrative privileges and so on, right? So addresses of handlers are defined in the trap table. So the only other way to enter the kernel is to use interrupts. I will mention that later, right? But that's not alternative way to do that. So system calls, and which is a special case of traps, and interrupts, right? So traps and interrupts. That's the two ways that we can enter the OS. So typically, you just reserve one trap vector or specialist instructions in case of x86-64 for system calls. So now the system call itself, one system call can be distinguished from another system call by using a special index. Right, so 0 corresponds to one system call, 1 corresponds to a different system call, 2 corresponds to yet another system call, and so on, right? So it's kind of like, think of it as just some first argument to a function, right? But fundamentally, you're calling just the same function or the same trap vector. So I think we actually answered some of these questions. Why do we need a kernel stack, right? Because we cannot rely on user stack, right? So that's the reason why we want to do that. So, but who is going to switch kernel to kernel stack? Remember, in the picture, hardware is doing it, right? Not the operating system. It's not the trap handler that is switching to kernel stack. Why is that? Any guesses? What? So, okay, go ahead.
Other scenarios, and then trap handler, so we're gonna switch to kernel stack.
Yes, true. Like, for example, interrupts, right? But let's just put it aside for a moment. But let's just put it aside for a moment. Is there any reason why? Let's just forget about other scenarios. Let's just say we just have only traps. Why can't we just do it in a trap handler? Why can't I just say, let me overwrite RSP in a trap handler to something else? So RSP would be the stack pointer register, right? So why can't I just go and do the very first thing in the trap handler? Well, because the reason why we already have to save some information, we already have to save the program counter, we already have to save the user stack pointer, right? So we cannot, I mean, at the very least, we need to save the program counter somewhere, right? So where are we going to do that? I mean, we cannot use any registers for that. Because the program may not be even suspecting that it's doing anything bad, right? Maybe, as I said, system calls is not one example. Here, at least you are aware that you are going to issue a trap. But in some cases, like whenever some non-fatal traps, like when you lazily allocate memory, the program is not even aware that this instruction is causing some trap. So it's not prepared to see any damage in its registers. So it doesn't really save and restore its registers. So we cannot even use any registers to put this program counter. We have to already keep it somewhere, and we're going to keep it on stack, right? So, but we cannot use user stack for that because that's potentially unsafe. So therefore, the hardware itself, the CPU itself, has to switch to kernel stack even before we call the trap handler. So I think that's this is really important to note here, right? This is why you can see that the save and restore happens by hardware, right? So the textbook is not super precise here. It says that you save and restore all registers. That's not true. Nowadays, you will only save, as I said, some specific registers such as program counter, maybe some other important program state, but that's about it, right? Maybe you will also save what kind of trap it is, so that you can get back to that information later, right? So, but again, that's not all registers. Other registers you can save and restore in the trap handler. That's not too late to do that at that point, right? So that's the very first thing you can do in your trap handler. But there is no, therefore, there is no actual point to do that by hardware anymore. I mean, historically, x86 supported hardware context switches where they would handle that automatically. But now in 64-bit processors and pretty much every other processor, we do it in software because we have better idea for this specific trap, what kind of registers I need to save and restore. So I can do it more fine-grained. So in the final question, who is going to save the instruction pointer and program pointer? Well, that should be done by the hardware, right? So that we already answered. And they have to be stored also on the kernel stack, not the user stack. Nothing should be stored on the user stack. Well, it's just basically we save the user stack pointer register and restore it. We don't care what value was there. Like if there was some garbage initially, the OS will not do anything at that point. That's up to user program to worry about this later. So that may cause some other issues down the road. But that's not our concern for this given trap yet, right? So, like I previously had a question whether int is privileged. Yeah, it's not privileged. You can look at this Wikipedia page as an example, or I think this one actually. Yeah, I think Wikipedia also has it. I don't remember if I took it from Wikipedia or from other source, right? But this doesn't matter fundamentally because you will find the same, pretty much the same information there. So you can see that there is it's maybe a little scary, but you can see that what errors this instruction can do. Like, and then it mentions general protection is something that you want to look at whenever you want to decide whether it's a privileged or unprivileged instruction. So it doesn't really say anything. In fact, if you are familiar with x86 architecture, you know that privilege level 3 corresponds to user mode. And if you read this table, you can see that it's actually totally fine that privilege level can be free, right? So there is no problem with that, right? So you can see if DPL is free, then this and that, right? So that means DPL free itself is not causing the problem, but something else may cause the problem, right? So therefore it's totally fine to execute it in user mode. Now compare that to a different instruction. So for example, invalidate a page. That's something that would manage memory, right? So virtual memory. So now you can see there is general protection, right? So it says if the current privilege level is not 0, so which means kernel mode in case of x86. So 0 kernel mode and 3 is user mode in case of x86. And 1 and 2, as I mentioned previously, they are not used by the vast majority of modern operating systems. So the current privilege level is not 0, therefore it will cause a fault, right? So that means it will have a corresponding trap handler. So you can look at these pages, like go to this website and it have a description for these instructions, right? So you can check that if you want. Likewise, there is some other maybe sources like other documentation that you want to look at. Again, this is not very likely that you will need it in this course much, but still, if you're curious, you can look at at least maybe for some project, maybe you will have to look at some manual, right? So, but I mean, not in too much detail. I guess for the second project, you will likely need to study some information in the Intel AMD manual, but that's just one small section there, not a big deal. But in general, if you are curious, you can read official Intel and AMD manuals, right? Or you can go to the website that I previously mentioned, has instructions. Also, things like Linux kernel, libc, there is a website you can go to and explore the source code there. So you don't necessarily need to download it. You can go to and look at this files through your web browser. So just, yeah, you still have a little bit time. Just let me complete it, maybe a couple of more slides. So just to clarify, so when I use kernel and OS, we'll use this terminology interchangeably. So sometimes OS refers to the entire distribution, like Linux distribution, Ubuntu, or Red Hat, or Fedora, or Debian. But remember that they're using the same OS kernel. There might be different versions, maybe slightly different patches, but they're using the same Linux kernel. So therefore, it's kind of fair to say that the OS kernel is the operating system, right? So but some people will disagree with this. Some people will say that some applications are also important, and therefore they're also part of the operating system. So it's a little bit trickier. I guess in this course, we will use OS and kernel interchangeably, right? So unless I specify it differently, when I say OS, I mean kernel. So now let's go back to question 2 before we wrap up. So the question 2 was, how does the OS get to start running here, right? So when we had a process A, like here, right? So what can happen here? So clearly one thing that we can do, we can issue a trap, right? So we already looked at this. This is the way to go back to the operating system. And specifically, we can call a system call, a schedule yield, and if processes are cooperating, they can yield sometime to each other, right? So they can run maybe for some time, then yield to a different process, and so on, right? That's one model, right? But another possibility is that process A is preempted. So we need some way outside of the process control to kind of go back to the operating system. What is this mechanism? Any clue? Like any ideas? So what is this condition? When the process was running too long, right? So when it was taking too much time. So how can I detect that it was running too like really long time? Okay, go ahead. Yes, not the clock, but the timer, right? So so there is a special device that we can have a timer, and a timer can trigger an interrupt. So the timer can be programmed such that maybe every 10 milliseconds it will trigger an interrupt, and then the OS will decide, do I need to run this process or do I need to switch? So by the way, milliseconds, that's like really ages for the operating system. That's a lot of time, right? So that's like I mean, that's like the operating system deals in nanoseconds, microseconds, right? Milliseconds, that's really a lot of time, right? A lot of things can happen during 1 millisecond. Okay, so so there must be a mechanism so that we can do that, right? So we will use an interrupt. The timer interrupt will periodically let the OS run, and then we can switch to the operating system. Okay, and just to wrap up, the last thing I wanted to mention here. So what are other examples of interrupts aside from timer? Like keystroke, when you type on the keyboard, that's another interrupt. Maybe mouse click, or disk completing or read and write operations, right? So that's like, you don't want to wait for your hard disk to complete an operation because your hard disk is really slow, right? You want to have some just notification mechanism, which is completely independent from CPU. Network packet, right? So maybe your phone is idle, right? But then after some time you get a notification, so because some packet has arrived, and that packet was woken up some program, like maybe you got an email or something like this, or maybe social network notification. So you saw some notification on your phone, but other than this, it was not using network, right? So you again have some sort of interrupt here. So interrupts are different from traps, right? So we will so because they're external.